Today we're going to look at lesson 90, and that's on section 10.2, Permutations and Combinations. I'm calling it Learning to Count. So we're going to be practicing multiplication principal counting, permutations, combinations, all sorts of stuff. But before we get any further, I need to talk about factorial. So factorial is a mathematical symbol. It's represented with an exclamation point, and it's defined as follows. 0 factorial is equal to 1. This is important, and I'm going to come back to why 0 factorial is equal to 1 in a little bit. 1 factorial is 1, and then n factorial is n times n minus 1 times n minus 2 times n minus 3 times all the way down to 3 times 2 times 1. And I have here if n is greater than 2 because you wouldn't want to have any negative numbers there. So if I'm talking about 5 factorial, well, that's really 5 times 4 times 3 times 2 times 1. Okay? So you can do that out in the calculator by doing 5 times 4 times 3 times 2 times 1. Really, times 1 doesn't need to be typed in. It is 120. So that's method 1, literally typing into the calculator. But if I asked you like 16 factorial, I don't really want to type all of that into my calculator. So I'm going to show you another way to do it. And I'll do it with 5, and then we'll do it with 16 as well. So we're going to go into math and over here to PRB. PRB stands for probability. And then I want number 4 there. So that's how I can get that factorial. So as a reminder, that factorial symbol was math over to PRB, and then it was number 4. So if I wanted to find 16 factorial, and we're going to use that a ton today, that factorial symbol. 16 factorial, type in 16. I'm going to go math over to probability, and I want number 4. Yeah, factorials get large very, very quickly, FYI. Oh, what just happened there? Oh, what happened? All right, well, my 16 factorial got shooting down. I don't know why. 2.092 times 10 to the 13. Now I have one more thing here, and I have 90 factorial divided by 92 factorial. Okay, so 90 factorial. Dun, 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 dun. Overflow. Oh, man. So that means I can't actually do this. So we are not going to think that it's impossible, though, before you start to go down that rabbit hole. See, and even that overflows. So think about what we're doing here. Well, 90 factorial, that's 90 times 89 times 88 times 87 times all the way down times 3 times 2 times 1. And 92 factorial, well, that's 92 times 91 times 90 times 89 times 88. Oh, so seeing what I'm seeing. So as we take a look at this, the 90s can cancel out. The 89s can cancel out. The 88s can cancel out. The 87s cancel out. All of the ones in between cancel out. The 3s, the 2s, and I guess we'll cancel the 1s too, because even though they don't do anything, I'll still. So on the top here, I'm left with 1. On the bottom, I have 92 times 91. So really just 2 times 91. 1 over 8,372. So even though if we tried to evaluate 90 factorial or 92 factorial and it wouldn't work, we can still manipulate these to work with them. So what we're going to look at in today's lesson and the next lesson is Combinatorics, which is a branch of mathematics involving counting techniques. So the first problem I want to look at is that ice cream sundaes come in 5 flavors of ice cream. You can have either whipped cream or no whipped cream, and 4 possible toppings. How many different sundaes can be made with only one flavor? So we're not mixing any of the flavors up, okay? And only one topping, okay? And that's not counting the whipped cream because, you know, it's got to have whipped cream. So I have 5 choices for the ice cream. You can either have whipped cream or not whipped cream. And then for my toppings, so that's probably like hot fudge, butterscotch, um, maybe like sprinkles and a cherry. Okay, those are our 4 possible toppings. So that's 4 options there. So basically we're talking about like that I could have mint chocolate chip with whipped cream and a cherry. Or I could have mint chocolate chip with whipped cream and sprinkles. I'm not going to write out all of the options. Mint chocolate chip, whipped cream, and chocolate syrup. Now, in fairness, there are combinations that would not go together. Like, I would not do mint chocolate chip with butterscotch or caramel topping. It's not a good idea. However, we're still going to calculate them. So the number of options that are available are 5 choices for the ice cream. So that's this first spot. Whipped cream or no whipped cream. So I could have mint chocolate chip, no whipped cream, and cherry. That would be another option. Okay, so cream. So 5 options for this first spot, 2 options for this, 4 options for there. Going to give me 40 possible sundaes that are available. Another way to visualize this would be a tree diagram. So it's like I could have vanilla, chocolate, mint chocolate chip, coffee. I'm writing out coffee because I don't want to confuse it with chocolate. And I guess cookie dough. Or actually cookies and cream. Very important decisions here. Then off of each of these I have 2 branches, and that's for whipped cream or no whipped cream. And then from this I have 4 branches for all of those. Now this is going to be kind of messy, so I'm not going to go all the way through the whole thing. But if you actually had the time and made it and it didn't get too messy, you could count up how many different paths you could take for this. Okay, but that gives you an idea of what a tree diagram would kind of look like. So you probably used it instinctively to count this up, but what we just used is called the counting principle of multiplication. If there are A ways for one activity to occur, that's our ice cream choice, and B ways for a second activity to occur, whipped cream or no whipped cream, then there are A times B ways for them both to occur. And then this one I had a third one, and we just multiply each one of those. Ms. Marhefke's car has a keypad lock on the outside with 5 buttons. True story. Her combination is 4 digits long. How many options are there if the numbers can repeat? So it's like I have A, B, C, D, and E, and I drew them as buttons. And I want to know how many different combinations can I make that are 4 digits long. Well, this first one, I could have A, B, C, or D, or E. There's 5 options. The next one, I'm allowing them to repeat. So I could have the passcode that's A. I don't know if that was 4 or 5, but whatever. So I still can have 5 on this one, 5 on the next button press, and 5 on the third. That's 625 different combinations. Now, how many are available if the numbers cannot repeat? So that would mean A is not a possibility. I would have to have A, B, C, D. Okay, so I'd have 5 for that first option. But now, whatever letter I've used or whatever button I've pressed for that first one, I can't repeat it. So then I would have 4 options available, and then I would have 3 options available, and then I would have 2 options available. See this decreasing setup? Very similar to a factorial. See how these are tied together. And so here that is 100. Come on. There we go. Sorry about that. 120 combinations. So just by not allowing that repetition, I have decreased it by 505 combinations. There must be 505 combinations that have some sort of duplication in it. All right, most newer Connecticut license plates consist of a 3-digit number followed by 3 uppercase letters, such as 867KAT. The license plate, issued from 1976 to 1978, consisted of 2 letters followed by 4 numbers, NC 2020. If the numerical part of either plate never begins with a 0, how many more of the newer plates are available than were under the old system? So let's do newer here in the old system. So our newer one, they both have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. They both have 6 spots. So our newer one is number, 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 letter, letter, letter. And our old system was 2 letters and then 4 numbers. Okay. And this numerical part does not start with a 0. So no 0 on either of those. Okay. So even in my example here, NC 2020, we're allowing repetition. Okay. Okay. So how many digits are there not including 0? Well, I could have 1, 2, 3, 4, 5, 6, 7, 8, or 9. So there's 9 options here. If I'm including 0, then I have 10 for this one, 10 for this one. Again, we're allowing repetition. There are 26 letters in the alphabet. 26, 26. There was no restrictions on the number which letters were involved in our license plate. Now, I'm going to put my disclaimer that the DMV probably does have restrictions that you can't make certain words up, and I'm sure you could insert whatever ones you would like there, that there are certain things they won't allow you. I'm certain of it. Not going into it though right now. 26, 26, 26. Boom. So I have, these are how many license plates are available under this new system, 15,818,400. Now in the old system, we had our 2 letters for 26. The first number not being a 0, and then any number on the last ones. And so 26 times 26 times 9 times 10 to the third. I'm just going to use an exponent on that. And so my question, however, move these out of the way so we can actually read the question. How many more are available under that comparatively? So I'm going to subtract them. So these both examples, my keypad lock on my car and the license plate example, are both called permutations. Permutations are an arrangement of items in a particular order. So the keypad is a permutation because it has to be pressed in the correct order. So if my passcode is ABCD, if you type in DABC, you will, even though it has the right letters, it's not going to count, it's not going to open the door. So the order that I type them in matters. The license plate also, the order that the letters and the numbers are on the license plate matter. It distinguishes between different cars. Other things that the order matters, a telephone number, okay? Because if you switch 2 digits, you're going to call someone else, okay? There's tons and tons of things. So when I have repetition allowed, okay, so are objects chosen from n objects where the n objects are distinct and repetition is allowed. So that's like my being able to press the same button again, okay? I'm allowed to make my pattern, my combo be A, or my password. A password on a computer is another good permutation, okay? I'm allowed to repeat them, and I don't lock it out. It's going to be N the R. Okay? And you saw that. 5 to the 4th. All right. So how many ways can we arrange 12 books on a bookshelf? Now, here's where the repetition comes into play. There's going to be 2 different types of repetition between the 2 lessons. I cannot place the same book in 2 different spots if I only have. So Once a book is placed on the shelf, it obviously can't be put in another spot because it's already physically taken out. So I'm not going to do repetition. Now, where this is going to have nuances is the next lesson, and that's if I have two copies of the same book. I have two of my Algebra 2 textbook that are indistinguishable. Okay, we're not talking about that yet, but it will come up eventually. So how many ways can we arrange 12 distinct books on a bookshelf? Okay, so, sorry. Well, that first one I have 12 options. Now I've placed one book in that spot, so now I'm down to 11, then 10, and 9, and 8, and 7, and 6, and 5, 4, and then 3, and then 2, and then 1. Because that last book, I have only one option. It's whatever one is left in my pile. So it's actually 12 factorial. Okay, so 12, and that's math over to probability number 4. A very large number. Try again. So there are, let's see, 479,001,600 ways to arrange those 12 books on a bookshelf. That's 12 distinct books all being placed on the bookshelf. How many ways can we arrange 7 distinct books on a bookshelf from that same selection of 12? Well, so this is our first book, second, third, fourth, fifth, sixth, seventh. Okay, so I have 12 choices for the first book, 11 choices for the next book, 10, 9, 8, 7, 6. Now we stop there because we're only choosing 7 books in total. Not all 12 books are being used. So here we're going to have 12 times 11 times 10 times 9 times 8 times 7 times 6. Okay. So significantly smaller. 3,991,680. Again, still a ton, but significantly smaller. And it's smaller because I've basically gotten rid of those. Okay, so I have a number that is 120th of the previous one. Okay, so when calculating a permutation without repetition is given by the formula of n factorial divided by n minus r factorial. An alternate notation is sometimes you see this p of n comma r. So let's go back to the previous two examples and we'll do them with this formula. Well, this would be 12 factorial over 12 minus 7 factorial. 12 factorial over 5 factorial. There are parentheses around that, so you need to make sure you do that subtraction first, and it does not distribute. So 12 factorial divided by 5 factorial. There's that same answer because I have eliminated these options. Okay, and the way we would write this is 12p7. Now, how many ways could we do 12 books on a bookshelf? Well, that's 12p12. I'm using all 12 books. So using our formula, I'm going to get 12 factorial on the top over 12 minus 12 factorial. 12 factorial over 0 factorial. 0 factorial. That's pretty weird. 0 factorial, as we defined at the beginning, is just 1. And 0 factorial is 1 because there is one way to have no books on our shelf. You just have no books on the shelf. All right, so and another alternate notation here is P and R like that. So we're talking about from a selection and objects, selecting R of them. considering the order. So again, that considering the order is talking about that the order matters, that we, like a telephone number or a password on a phone or passcode on a phone, things like that. So 15p4, just straight computation. 15 minus 4 is 11. Okay, so I have 15 factorial divided by 11 factorial. If you have it typed in already like that, you can do second enter to just copy and paste 15 factorial over 11 factorial. 12 skiers are competing in the final round of the Olympic freestyle skiing aerial competition. In how many different ways can 3 of the skiers finish first, second, and third to win the gold, silver, and bronze medals? Well, here the order matters because getting gold medal and versus bronze is different. And I have 12, and so this is really 12, and I want to pick 3. So 12 factorial over 9 factorial, which is 12 factorial over 9 factorial, 1,320. So a combination is a selection in which the order doesn't matter. So if I was going to adjust example 7, I'd have 12 skiers. How many ways can I have them 3 winners without considering order, or that the 3 winners are all going to get a prize, the same prize? Okay, so when calculating a combination without repetition, it's given by the formula. There's less ways. So a very similar formula, but it has additional r factorial. And you have your alternate notations down there below. So Mrs. Marhepke wants to pick one group of 3 students out of our class of 22 students. How many different groups of 3 can she form? Well, it doesn't matter if my group is Andrew, Zoe, and Andrew, Zoe, and then Lauren versus Lauren, Andrew, Zoe. That is still the same group. So the order here doesn't matter. This is going to make it a combination. So of our 22, I want to choose 22 factorial over factorial 3 factorial. One thing about how I'm going to type this in the calculator, you need to make sure that this denominator has parentheses around it, because otherwise it's going to divide by the 19 factorial and then multiply by the 3 factorial. So this is right now the correct way to type it in. Okay, and I'll show you without the parentheses so you can see. If I don't have my parentheses, way different answer. Okay, so it's really important that you put those parentheses. 1,500. And this would be groups. So why was the previous question a combination instead of a permutation? Because the order that I was selecting the students didn't matter. It was still making the same group of 3. How can we change it to a permutation? You would have to have assigned roles. So maybe it's president or the recorder, timekeeper, and brainstormer. Whatever roles are being assigned to the group, or president, vice president, treasurer, because that would make a difference of what job you're doing, which would create a permutation. So a combination is picking a team of 3 from a group of 10. Permutation would be picking a president, vice president, and water boy from a group of 10. Combination, choosing 3 desserts from a menu of 10. Permutation, listing your 3 favorite desserts in order. My favorite is cheesecake, and then this, and then that, from a menu of 10. So Indicate whether the problem is a combination or permutation, then solve the problem. Professor Indiana Jones gives his class 20 essay questions to review for their midterm. How many ways can he select 8 essay questions? Yikes, 8 essay questions to make up the test without considering order. So those are the important pieces. He's got 20 to choose from. He's choosing, I'm doing a combination here because of the without considering order. 8 20 factorial, 12 factorial, 8 factorial. I want the one with the parentheses if you're using the copy and paste strategy. 20 over 12 factorial, 8 factorial. Boom. All right. So that's how many different tests would be available for him without concern about what order they were in. A multiple choice test would probably be more of a permutation because the order of the questions. Baskin-Robbins offers 31 different flavors of ice cream. We want a dish with 3 different flavors. How many different bowls of ice cream can we make? We're not going to, so a couple of nuances here. We are not going to worry about combinations that wouldn't go well together. So we're not going to worry like cotton candy and Rocky Road don't mix well. True, moving on. It's still a possibility you could order, even if it's not an appetizing combination. We're also not going to worry about if what order the ice cream is placed into the container because you still have the 3 scoops of 3 different flavors. So whether I put chocolate, vanilla, and then peanut butter ice cream or peanut butter, chocolate, and then vanilla, it's still going to give me the same bowl of ice cream. So I'm not going to take into account order here. So I want of my 31 C. And so I'm going to show you another trick with the calculator. You can also do a combination at 31 math. As you go back to that probability, you've probably been in that a few times without factorial. You can actually use this NCR for combination as well. So it's number 3. 3 and get 4,495. So continuing on for a moment, how many ways can we select 1, 2, or 3 different flavors of flavored scoops of ice cream at Baskin-Robbins? Because maybe I don't want 3 different flavors. Maybe I just want 3 scoops of vanilla or 2 scoops of chocolate, things like that. Well, or just chocolate and vanilla. So I would have my 31 choose 3 because that's 3 different flavors. 31 choose 2 and 31 choose 1. Well, 31 choose 3. That's at 4,495. Just calculate that. 31 choose 2. To copy and paste. 465. And then 31 choose 1. How many ways can I choose one item? Well, of the 31, there's 31 ways. That's right there. Boom, 31. Okay. So I'm going to now take these values and add them up because it's 1 or 2 or 3. So those ors look like addition signs. Oops, should be a 1 at the end. I typed in 32 instead of 31. There we go. Okay. All right, your lockers are a dial combination lock with a dial that has 40 tick marks representing the numbers 0 to 39. The lock is opened by turning the dial to the right, then to the left, and then to the right, stopping each time at the corresponding number of a 3-number code. How many different 3-number combinations are possible for this type of lock? I left this problem for the last. First thing asked, is it a permutation or a combination? Now, you might want to call it a combination because I said the word combination multiple times in this problem, but it's actually a permutation because again, if a you put your combo in a different order, it's not going to work. The order matters that I type the numbers in. That's what creates it as a permutation. Okay, so a combination lock is really a misnomer. This really should be a permutation lock. Will it make a difference if the numbers can repeat or not? Of course. So calculating both. So if repetition is allowed, so that would allow the combo of 40, 40, 40. Then the first one has 40 options, the next one has 40 options, the third one has 40 options. If we're not allowing any repetition, I would have 40 options here, 39 options here, and 38 options here. So this is going to be 64,000, sorry. And 40 times 39 times 38 is 9,200. This concludes our lesson on combinations and permutations.